Welcome to Dr. Sherry's Astronomy channel. This time, the theme is, XRISM satellite captures the plasma winds from a unique X-ray binary. The XRISM satellite, launched on September 7, 2023, is a state-of-the-art X-ray satellite led by Japan. It is equipped with two observation instruments, Resolve and Extend. The satellite is designed to observe celestial bodies in extreme environments, such as black holes and galaxy clusters, capturing information about their temperature, density, chemical composition, and motion. To enable observations of these extreme environments, XRISM specializes in X-ray spectroscopic observations and is equipped with the world's highest level of spectral power. Since the dawn of X-ray astronomy in the 1960s, Japan has always been at the forefront of advancing global X-ray astronomy. While not often in the spotlight, Japan's focus has been on spectroscopic observations, which provide more detailed physical information than simple images. XRISM continues this tradition of Japan's leadership in X-ray astronomy, offering an X-ray satellite with unparalleled spectroscopic power. There are four main ways to observe light from space. The most popular method is imaging, with spectacular images from the Hubble and James Webb Space Telescopes. In X-ray observations, the Chandra satellite provides high-resolution images comparable to visible light observations. However, information from imaging alone is limited, so to extract detailed physical data, spectroscopic observations, which analyze light by its wavelength, are necessary. By taking a spectrum, we can observe phenomena such as redshifts that represent the expansion of the universe and emission lines from atoms and molecules at specific wavelengths. The James Webb Space Telescope also focuses on spectroscopic observations. For example, 9 out of its 17 observation modes are spectroscopic. Furthermore, by repeatedly observing the same celestial object over time, we can detect temporal variations. For example, quick observations of the Crab Nebula reveal periodic pulses every 33 milliseconds. The final observational method is polarization. Polarization refers to the directionality of light waves. In X-rays, NASA's XRISM satellite, launched in December 2021, is capable of observing polarization from various celestial objects. The Japanese X-ray astronomy team provided key technologies for the XRISM satellite. These four types of observations have their own strengths and limitations based on wavelength and equipment. For example, some telescopes can only take images. While NASA's Chandra satellite emphasizes imaging, Japan's XRISM satellite prioritizes spectroscopic observations. Let's compare the features of the XRISM satellite with other active X-ray astronomy satellites. It would be ideal to build an X-ray satellite similar to the James Webb Space Telescope, which costs over yen 1 trillion and is enormous. However, due to budget and scale constraints, each satellite has its own characteristics. Here, we compare 5 features across 3 different satellites. While this comparison does not include all satellites, NASA's XRISM, which observes X-ray polarization, also offers a unique feature. Spatial resolution refers to the resolution of an image, and NASA's Chandra satellite is exceptional in this aspect. The field of view is nearly the same for all satellites. NASA's NuSTAR satellite is the only one capable of observing X-rays above 10 keV. The Newton satellite boasts tremendous light gathering power. XRISM, on the other hand, has both high light gathering power and unmatched spectroscopic capability. The direction XRISM is taking with its spectroscopic power aligns with the groundbreaking achievements of the James Webb Space Telescope in resolving cosmic mysteries. The XRISM satellite has a period called the Initial Performance Verification Period, which is set after the launch to demonstrate the satellite and observation equipment's capabilities. During this period, various celestial bodies are observed to evaluate the satellite's performance, and at the same time, the first scientific results are produced. The results of Cygnus X3, which were recently announced, were also observed during the initial performance verification period in March 2024. Cygnus X3 is a binary star system located about 30,000 light-years away in the direction of the Cygnus constellation, shining brightly in the summer night sky. A binary star system is a group of two or more stars that are bound together by gravity, orbiting a common center. While our solar system revolves around a single star, the Sun, many stars in the universe are part of binary systems. Binary systems often trigger extreme phenomena during their formation and evolution. For example, one of the most extreme events is when two black holes form a binary system, and their merger generates gravitational waves. Understanding the formation and evolution of binary stars is crucial for understanding the history of the universe. Cygnus X3 consists of a massive Wolf-Rayet star as the primary star and a companion star that is likely a compact object, either a black hole or a neutron star. The Wolf-Rayet star is an extremely massive star that releases vast amounts of gas each year, equivalent to the mass of several Earths. This gas forms a strong stellar wind. The companion star is thought to be either a black hole or a neutron star. Thus, this system likely began as a massive star, which later went through a supernova explosion, leading to the current state of the binary system. As it continues to evolve, it could eventually become a binary system of black holes, emitting intense gravitational waves. The two stars in this binary system are extremely close, with an orbital period of only 4.8 hours. Some of the massive gas released by the Wolf-Rayet star is drawn in by the companion star's strong gravity, forming an accretion disk. As the gas falls in, jets are ejected, creating intense gamma rays. Chandra's images have revealed a mysterious X-ray object that appears to be a cloud near the system. This cloud acts as a mirror, reflecting some of the X-rays from Cygnus X3 back toward Earth. Due to the short, 4.8-hour fluctuations typically seen in X-ray binaries, this object has been nicknamed Little Friend. To uncover the identity of this little friend, observations were made using the radio telescope SMA on Mauna Kea, Hawaii, which detected a corresponding radio source and jets. The radio source was identified as Bok globule, a small, dense, and very cold cloud where stars may form. When combined with X-ray images, we see the jets in blue and red, showing the motion of the material. The blue jets are moving toward Earth, while the red jets are moving away. Thus, Cygnus X3 is influencing the environment around it, even triggering the formation of new stars. XRISM is observing regions extremely close to compact objects, which have significant influence on their surroundings. While these regions may appear as points in images, XRISM's spectroscopic capabilities allow us to map out these regions in detail. The image shows how the gas released by the Wolf-Rayet star is drawn in by the gravitational pull of the compact object, presumed to be a black hole, emitting intense X-rays. The gas forms an accretion disk, and surrounding it is a hot plasma region known as the corona, from which X-rays are emitted. The energy emitted per second in X-rays is equivalent to several days' worth of energy radiated by the Sun. When this X-ray radiation ionizes the surrounding gas, it creates what is known as photonized plasma. XRISM has captured highly detailed spectra of this photonized plasma. The horizontal axis represents the energy of the X-rays, while the vertical axis represents the count rate. In X-ray astronomy, light is treated as particles, and each photon's energy is plotted on the horizontal axis. Although we can convert this energy into wavelength or frequency, X-ray astronomy typically displays it in terms of energy. This spectrum shows the energy range from 6 to 8 keV, dominated by iron ions. The vertical axis indicates the rate at which photons with this energy arrive per second. The lower panel shows spectra obtained by XRISM, while the upper panel shows spectra from NASA's flagship Chandra satellite. Thanks to XRISM's superior spectroscopic power, it has captured absorption lines and emission lines from various iron ions, which were previously undetected. By examining this spectrum, we can capture the detailed motions of the stellar wind from the Wolf-Rayet star and the gas falling into the compact object. For example, the iron emission line detected around 7 keV comes from the most highly ionized plasma, reflecting the extreme conditions near the black hole. Since ionizing material requires high energy, this suggests the environment around the black hole. This diagram shows the changes in the spectrum due to the orbital motion of celestial bodies. On the right, the position relationship between the Wolf-Rayet star and the compact object as seen from the XRISM satellite is illustrated. It can be observed that the strength of the iron emission lines fluctuates as the orbit progresses. Near the compact object emitting X-rays, particularly intense photonization is occurring, and it has become clear that the iron ions are being dragged along by the compact object's orbital motion, moving at speeds of several hundred kilometers per second. The data from this observation was taken during XRISM's early performance verification period. Not only has it demonstrated the satellite's exceptional performance, but it also confirms that XRISM can capture the active behavior occurring in the close vicinity of celestial objects that appear as mere points in images. Cygnus X3 is expected to eventually evolve, with the Wolf-Rayet star undergoing a supernova explosion and becoming a black hole. It could then form a binary system of black holes, known as a gravitational wave source. As XRISM continues to collect data, we can expect to unravel the processes that formed this fascinating celestial object and trace its future evolution. Thank you for watching, and I'll see you in the next video. If you enjoyed this video, please don't forget to give it a thumbs up. Hit the subscribe button and the notification bell icon, so you'll be notified when new videos are released.